Welcome back, and in this lesson we're going to be going over the notation of time complexity. Now it's important to note that when we talk about the notation here, the notation is usually applied to time complexity, but it can still apply to other situations. Unless otherwise stated, it is time complexity, but the same notation means the same stuff if we use it in space, memory, or even cost, or in any other field complexity. For example, you could use this inside of baking to say that this is the maximum amount of time it'll take to make a pie. With that in mind, let's start going into notation. The first thing we have to note is that there is a big O, and that is actually the name of the notation. Capital O is called big O notation, and whatever is inside of the parentheses is what the big O notation represents. So in this case, it says big O n. This means we have the worst case time as linear time. This means that the upper bound for the growth rate is linear. What this means basically is that if it took 20 seconds to process 10 values for some algorithm that does some task, we don't care, then if we put in 20 values, it'll take double that previous amount of time, so 20 seconds. So we have to make sure that when we have ON time, we keep in mind that the growth rate will be linear. Now, again, we have different types of growth rates here. So we also have O n squared, which is quadratic growth rate, or O log n, which is logarithmic growth. This basically says that, well, if you were to model the growth rate and you were to model the amount of time it'll take to if you increase the number of values or decrease the number of values, the amount of time it would take could be plotted as either quadratic, as a quadratic equation, or as a logarithmic equation. You'll also note here that we're dropping any other constants or any other values. So for example, it doesn't say O 5n squared, it says O of n squared. This is always going to be the case. We ignore any constants. O of 5n squared is treated the same way as O of n squared or O of 60n squared. What we care about is the dominant term here. Remember, the dominant term is the one that actually causes the growth rate. For example, you could have a more complex growth rate that could be described as O of n squared plus n plus 1. All it would be called is O of n squared, because again, we only care about dominant terms and we ignore any constants. Now, we also have O of 1, which is constant time. Constant time is a little bit difficult for some people to imagine, but imagine constant time as basically some constant we don't care to articulate. So for example, constant time describes the amount of time it takes to insert a value into an array. If you had to insert a value into an array at index 5, at index 60, and no matter what the object itself is or how big that object is, it's always going to be a constant amount of time. It won't change depending on how full the array is or anything else. So for this, we use constant time. Constant time also means other stuff. It can basically mean anything that we don't want to describe but is part of the equation and needs to be mentioned. For example, if we were copying a series of values, then the constant time, or O1 time, could be used to describe the amount of time it takes to extract a value and to paste that value back into the array. So we have to make sure that some things are always going to be constant time, like arrays or copying or comparisons are always constant time. This is extremely useful and will be frequently used in the equations. We also have O of n to the n time, or exponential time. This is the worst efficient time. It takes the most amount of time and scales the worst. Because basically, if you started out at 5 to the 5th power is a pretty large value, about 3,125. But if you had, let's say, doubled that value and made it 10 to the 10th, 10 to the 10th is an extremely large value. It's 1 with 10 zeros after it. So remember this. When you have exponential time, it scales very, very poorly, and that scaling manifests itself really quickly. So in general, we want to avoid exponential time and bias ourselves towards constant time and logarithmic time. These are better than the alternatives, and we basically want to pick the most efficient algorithm possible. That basically means the lowest O notation time. As we mentioned before, O notation will ignore any constants, so O of 5n is considered the same thing as O of n and will be written as O of n, and only has the dominant term. So in that previous example of, let's say we said O to the n squared plus O to the n, O of n to the n plus O of n plus O of 1, we only care about O to the n O of n to the n, or exponential time, because again, this is the dominant term. If you've ever taken any sort of calculus where all you cared about was the ultimate result and the limit, that's the same thing as what we're going to talk about here. Now, we also have two other forms of notation. These are used the same way, but just mean something else. In our case, if we have, instead of O notation, which is the worst case time, which provides that upper bound for growth rate, if we use omega notation, and it again is called the omega n, for example, that's the lower bound, and that's the best case scenario. So at best, it'll scale linearly if it were omega of n. This notation isn't that useful most of the time because, again, we need to care about the worst case scenario. It's much more useful to have a worst case scenario to give to the client than to give them a best case scenario, since most of the time they want to have contingency plans for the worst possible situation, what takes the most possible time. A struck through O is for tightly bound. This basically means that if we have an average case time complexity. Remember, as we talked about before, we want to use the average case complexity whenever possible because it's the most descriptive and it's the best one. So if you have the struck through O notation, you should use that every single time. As a quick little side note, in some places you'll see that they won't always use these notations, and instead they'll use word notations. They'll simply say the best case time is linear time. In that case, best case can always be substituted in for omega, average case can always be substituted in for the struck through O, and worst case can always be substituted for the O of n notation. And then we also have to talk about recurrence relationships. Recurrence equations or relationships are basically a mathematical way to express time complexity. So for example, that previous example where I said O of n squared plus n to the n plus 1, that's a recurrence relationship. We basically say that, well, let's break down how the time complexity was formed. These are mostly used in academic settings, since most of the time, all the average programmer cares about and all that we care about is what is the complexity. We don't really care about how we came to that. We will describe some of the basics of how we came to it, but in academic settings, it's proved very, very rigorously. But it's important because otherwise we have no way to communicate. This gives us a constant way to say, well, this is the exact amount of time it'll take. Recurrence relationships are useful because they allow us to break down the problem into subproblems. For example, if it takes O(n) time to solve one problem, then to solve half of each of the subproblems, if there were two subproblems, would take O of n over 2 time, and that times 2. So again, we have to consider that recurrence relationships still use the O notation of before, but because the O notation can drop some of those constants, there is some gray area in there, and most of the time we'll try to bias ourselves to one side. We'll either use a strict O notation, and when we mention recurrence relationships, we'll make it very, very clear. Now, efficient algorithms usually have a drawback that gets ignored in the recurrence relationship. This basically means that if we have an algorithm that, let's say, we have 3 algorithms for sorting. One scales at O of n to the n, one scales at 5n, and one scales at O n. In all 3 of these cases, we have to consider the constants that are being ignored. With the n to the n, that's obviously worse, so we can strike that out at first. But 5n and n are going to be treated the same way by O notation. So keep in mind that when you see an algorithm, you have to understand how it works as well. You can't just look at the O notation or the notation and the recurrence relationship and expect to know which algorithm will work best, because many times they'll drop some of the subtleties, and especially with O notation, they'll ignore the fact that some real-life optimizations can be performed, and in some cases, in reality, one algorithm will always be faster, even if they have the same O notation when they're written out. Finally, we'll talk about the different styles of algorithms. There's 4 main styles of algorithms we're going to be covering in this course. First, we have the brute force method. This brute force method basically uses the power of a computer to try each possible solution. Let's say you forgot your passcode to your home, and you had a possible range of values from 0 to 999. The brute force solution would be to try 0, 1, 2, 3, until you either find the number or hit 999. Now, this is clearly inefficient, but it's very quick to build, and many times, because our computers can perform billions of calculations per second, it doesn't really matter. This is how randomness works, actually. So, brute force solutions, they work well, but they're the quick and dirty solution. Usually, if you want to push something to the client or you want to use something in an actual application, you want to avoid brute force algorithms because they don't work as cleanly. Greedy algorithms basically say that, well, many times the best solution can be found by creating good solutions to all the subproblems. In summary, we basically say, well, let's say you had to go for a grocery shopping trip, and you had to buy the lowest cost total for your groceries. Let's say you had to get bread, milk, and vegetables. You would basically say that, well, the lowest cost overall will be found if I find the lowest cost items in each category. So I find the lowest cost bread, the lowest cost vegetables, and the lowest cost milk. Combining all of these will find the lowest cost overall grocery bill. So in that same way, greedy algorithms say that, well, the smaller solutions to each of the subproblems that we break the bigger problem into, if we optimally solve all the subproblems, we'll come up with the best solution for the big problem. Divide and conquer algorithms basically say that, well, we have one big problem, let's break that problem into smaller bite-sized chunks that we can actually solve. For example, let's say you had to search 100 square miles for a key. You wouldn't search 100 square miles because you don't know where to start. Instead, you would say that, well, let's start in one spot, see if we can search there, and then keep breaking it into smaller and smaller chunks until we can actually use this situation. So we basically take the bigger problem and break it into smaller problems until we have small problems we know how to solve, at which point we're done. So for example, to go back to that grocery analogy, you're buying your groceries and you say, well, I have to go grocery shopping. What does that entail? I have to buy bread, vegetables, and milk. After that, you say, okay, what type of milk, what type of bread, what type of vegetables? And you keep on breaking it apart until you reach one easy-to-solve subproblem, like saying, I need to buy brand X's milk. So then you know exactly how to buy brand X's milk, and then you're done. And then you can combine all the subproblems to solve the major overall problem. Most of the time, you will need recurrence to solve these problems. If you don't know what recurrence is, feel free to check out our lessons on recurrence because that will help clarify the matter. But it basically says that, well, we have a bigger problem and we're going to keep calling the same solution type until we break it into that bite-sized chunk. Dynamic solutions are basically divide and conquer algorithms, but instead of just solving the problems, we try to intelligently solve the problems. So we take the fact that many times the subproblems are repeats. For example, if you had to do grocery shopping for a week, many times the grocery shopping is going to recur. It's going to repeat itself. So you say that, well, I need to buy bread for Monday, I need to buy bread for Tuesday, I need to buy bread for Wednesday. Instead of buying bread each time and always having to take the most circuitous and taking a very long route, we instead say, well, I need to buy 3 loaves of bread. So you basically stored the solution to a subproblem, therefore you can speed up some of the solutions. The disadvantage of dynamic solutions is that they usually take a little bit more space, but they do tend to be faster than any other type of problem solution we have. So if you have a choice between a dynamic and divide and conquer algorithm, you should usually pick the dynamic one because it's the same type of solution as divide and conquer, but will store and therefore optimize some of the solutions. So hopefully you enjoyed the lesson. To summarize, we talked about the notation. We talked about how big O notation basically refers to the worst case time. We talked about the various forms and the most common types of big O notation, those being linear, quadratic, logarithmic, exponential, and constant time. We talked about how we ignore constants and only use the dominant terms. We talked about how average case is represented by the struck through O, and the best case is represented by the omega. We talked about recurrence relationships and how they're used in academia to represent the proofs of why an algorithm might take O(n) time, and why, while we won't use them that often, you can't just look at the recurrence relationship because it'll drop some important ideas. And then we talked about the 4 major styles of algorithms, and we talked about when you want to use each different type. So, hopefully you enjoyed this lesson. If you have any questions, feel free to private message me on Udemy or email me at my personal email. Hopefully you'll join us next time.